Okay, welcome to lecture. We're going to pick up where we left off there in sort of chapter 5 and 6. All right, so last time we were talking about reactions, and we started talking about balancing equations. Just a reminder, a couple important things about balancing equations. Obviously, when you have an equation, should be balanced. And when we do balance equations, as we talked about, essentially the only thing that we change are the coefficients. And again, those are the numbers that come in front of the formulas in a chemical equation. And obviously we want to keep changing those numbers until we get the same number of elements on each side of the arrow, our reactants and our products. Remember, we never change any of the subscripts, the little numbers in the formula, because obviously that changes what it is. And we never kind of insert any kind of big numbers in between the formulas or anything like that. So it's only the coefficients. And when an equation is properly balanced, as we talked about, two things should happen, I guess three. One, obviously, is we should have the same number of elements on each side of the arrow. Two, when you're done balancing the equation, all the coefficients do have to be whole numbers. And third, in addition to them being whole numbers, they do need to be the simplest set of whole numbers that you could do. So again, as we talked about, for example, if you had 2, 2, and 4 in terms of balancing an equation, you then could divide everybody by 2 and reduce everybody down. So sometimes that does happen. Sometimes people can kind of see a larger number. And again, if you could reduce everybody down by a common number to still get a whole numbers for those coefficients, you should do that. We also saw that if you have some equations there that contain those polyatomic ions, sometimes it's a little bit easier to kind of keep the polyatomic ions together and balance the equation with those things sort of as whole units. You can still go individual element by element, but sometimes with polyatomic ions, you get a lot more parentheses multiplying in and stuff like that. So sometimes it's just easier to kind of keep those guys together and then balance them together as whole units. We then started talking about types of reactions, and sort of the big type of reaction that we sort of started with was double displacement reactions. And again, that's sort of the big umbrella, if you will, of a class of reactions. And again, the way you can recognize those is you have basically two ionic compounds, and those positive guys end up switching partners on the other side. And when they switch partners, again, they form two new ionic compounds, and that's sort of your classic double displacement sort of reaction. Now, as I said, double displacement reaction is sort of like a big classification of ways that you could classify a particular type of reaction. We can even get more specific in terms of double displacement reactions and classify them even further. And that's sort of what we were talking about here at the end last time. And the first type of, really, it's a double displacement reaction, but it's also called a precipitation reaction, is one where you mix two solutions together and it forms some type of solid. And a solid is what is referred to as a precipitate, again, sometimes abbreviated PPT. And it is a result a lot of times of mixing actually two solutions. So again, two sort of in the liquid state solutions, aqueous state really, and some type of solid basically develops. So in addition to kind of predicting what goes on the product side, that's always what sort of happens, is just these two positive guys basically will switch partner. The other thing that we talked about that's important as well is the idea that when you do that, sometimes people try to balance the equation and also write the formulas at the same time. And that never really works well because you'll end up with formulas that are incorrect, and you'll be there all day trying to balance something that will never balance. So it's really important to do those things sort of in that order, or the proper order, So if you have just the reactants given to you and you need to predict the products, what you need to do is take the reactants, regardless of the balancing aspect of it, and just figure out what are the basic units that make up those things, and then put them together correctly, kind of like what we did with nomenclature, and get the correct formulas on the product side. Once you got pretty much the correct formulas and everything, it's at that point you could then go and actually balance the equation. So it's kind of write formulas first and then balance. Don't try to do both of them together because it usually will not end up really well. We also talked about three sort of types of equations that we can see, and that's sort of what we have scribbled on this page and we went over it last time. We do have the molecular equation, which basically is everybody written in the correct chemical formulas. We then can break apart that equation into another equation, which is sometimes referred to as the total ionic equation or the complete ionic equation. And pretty much in that equation, what we try to do is really describe what's going on in a particular reaction. So anything that's aqueous will be broken apart. We do keep together certain things, and anything that's a solid, anything that's a liquid keeps together or stays together, and anything that's a gas as well in most cases, and anything that's really a weak electrolyte. And that was something else that we talked about. There's strong electrolytes, right? And those guys 100% break apart in solution into ions. And when you have a strong electrolyte, you no longer have any of the whole unit still together. 100% of it is into ions. A weak electrolyte, on the other hand, mainly stays together when it's in solution, but is still able to produce a little bit of ions. And those are the ones that you see those reversible arrows, those arrows heading in both directions. And because it's still able to produce a little bit of ions like we talked about last time, it's still considered a electrolyte because it's able to conduct electricity. But again, nowhere near as good as a strong electrolyte, which 100% breaks apart. So that was like the light bulb example we looked at. A strong electrolyte will turn the light bulb on very brightly because there's a lot of ions floating around that solution. A weak electrolyte will still turn on the light bulb, even though it didn't produce as much ions, but a little bit of ions are being produced. And then we have a non-electrolyte, which will not produce any ions and not conduct electricity because of it. So because we have a weak electrolyte, we typically would not put it in our total ionic equation because it will mainly stay together. So we would put it in, but we wouldn't break it apart. So we would keep it together. And the last thing that we sort of talked about at the very end was, how do you know, when you make these combinations, are you going to get something that's solid or not solid? And that's what these solubility rules here help us with. And these are typical solubility rules of things that are soluble in water. And if something is found to be soluble, those are the guys that get the AQ symbol next to them when you write sort of the formula. If something is found to be insoluble, those are the guys that get the S symbol or the solid symbol next to them when you write the formula in an equation, for example. So here are some of those rules just to remind that are soluble in water. Pretty much group one, so lithium, sodium, potassium, ammonium, nitrate, and acetate, they're all soluble. So as we saw last time, as soon as you essentially see those guys in a formula, you pretty much could stop. You could go, okay, I know there's going to be aqueous. Really don't have to worry too much about it. Now we have chloride, bromide, and iodine. They also are typically soluble in everything, but there are three exceptions. And the three exceptions are silver, that's mercury 1, and lead. And the exception means that you do the opposite. So normally chloride, bromide, and iodine are soluble. So normally they get the AQ symbol. But if you have silver, mercury 1, or lead 2 in a formula with one of those guys, they go from being soluble to insoluble. So like silver chloride, I think was an example we saw yesterday. And that is chloride, which is normally soluble, but because it is hooked up with silver, it becomes insoluble. Sulfate, also soluble in everything except for some of those exceptions there, barium, calcium, and so forth. And then we saw these guys, which are ones that are typically insoluble. So these guys are typically guys that would have the solid symbol except if they have an exception, which is on the right-hand column there. So hydroxides are typically insoluble, except if it's pretty much like what we saw in the previous one, group 1, ammonium. Calcium, strontium, barium are slightly soluble, which again, as I mentioned, usually leans a little bit more towards the insoluble side of deciding. Sulfide, again, insoluble, except for group 1 and ammonium. And carbonate and phosphates are also insoluble typically, again, also for that major exception, which is basically what we saw in the last slide, group 1 and ammonium. Any questions on any of that stuff that we talked about last time? Okay, so I think this is where we left off. So I think we have some here. So why don't you take a moment or so, look through these, and based on the solubility rules, would you expect these guys to be soluble or insoluble in water? So just take a moment or two and we'll go over it. Okay, so let's take a look and see. So starting with the first one, we have potassium hydroxide. So again, remember, you may be able to find both things on the solubility chart. You may be able to find maybe one thing on the solubility chart. But really the key here, right, is we do see potassium, and potassium is pretty much group 1, and they are pretty much soluble in everything, which means that's almost as far as you need to go. You could also go to hydroxide, which we also saw in the table there, which is right there. And you can see that hydroxide is insoluble, except when it's with lithium, sodium, or potassium, which happens to be the case here. So we would expect KOH to be soluble, really because of potassium. But again, in this particular case, you could have looked at the hydroxide as well. Next, we have silver bromide, and bromides, again, are soluble in everything, except that there are 3 exceptions, and silver happens to be one of those exceptions, which means silver bromide would be insoluble because of that. Again, the silver making it an exception to normally bromide being soluble. On the next one here, we have calcium chloride. Again, here we could look at the chloride, and again, chloride is soluble in everything except for silver, lead, and mercury 1. And in this case, that does not appear to be in there since it's with calcium. So we would expect it to be soluble because of that. Next, we have lead 2 nitrate, and the key there is the nitrate. The nitrate, if you look back on that table, is pretty much soluble in everything. So there are no exceptions. So as soon as you see that nitrate, you do know that it is going to be soluble because of it. And lastly, we have lead 2 sulfate. So here we want to look at the sulfates, and the sulfates are going to be insoluble, even though sulfate is mostly soluble, but lead is one of those exceptions, and it would be insoluble. Any questions on any of that, or how to use solubility rules to determine sort of solubility? So usually the question I get is, do I need to know the solubility rules? And the answer is, you probably should have some familiarity with it. I probably will provide them to you in some form or not, but it's probably still good to have a sort of an understanding of them, at least a basic understanding of them. But they probably will appear somewhere, I assume. Any questions on any of that there? Okay. All right. So why don't you work on this one here? Write the equation for the precipitation reaction between potassium carbonate and nickel 2 chloride. So we'll see what you come up with. Take a moment or so. Okay, so let's take a look here. So remember, if you sort of have everything in words, you do want to make sure you just start with the right formulas to begin with. So we are the equation for the precipitation between potassium carbonate. So remember that potassium is K plus, carbonate is CO3 2 minus. So we should have K2CO3. We know that this is going to be soluble because it has potassium in it. So that will be that. Also because they tell us it's a solution, right? Nickel 2 chloride. So nickel would have a +2 charge. Chloride would have a -1 charge, which means we do need NiCl2. Also going to be aqueous because of chloride, not attached to silver, lead, or mercury. Again, in case you can't recognize this, this is our double displacement reaction. That's a positive negative guy. That's a positive negative guy. So again, these two positive guys are going to switch partners. When they switch partners, a reminder that you, even though there's some extra 2's and stuff in here, we want to get the right formulas first. So really this is K plus, right? And CO3 2 minus. This is nickel with a +2 charge and chloride with a -1 charge. So the K plus and the Cl minus are going to come together. And the basic units that make them up is +1 and -1, which means we just need one of each. And that would be the correct formula there, not K2Cl2, which is what a lot of people like to write. So this is the correct formula. We also want to do the same thing for our other two. This is nickel with a +2 charge. That's carbonate with a -2 charge. So when we put them together, NiCO3. So this again is what I was talking about earlier, that when you have to predict formulas or write formulas on the product side, it's important to get the correct formula first and then balance it. So clearly at this point, when I look at it, I am not balanced. And this is the point where I fix all those extra 2's by putting coefficients in front. So for example, I need perhaps a 2 there. It gives me my 2 potassiums on both sides. Also gives me my 2 Cl's on both sides. 1 nickel and 1 carbonate. I am then balanced at this point. So formulas first and then balance. Don't try to do both of them together, because you'll end up with something like K2Cl2, which is incorrect. We also want to think about solubility here, right? So again, potassium is soluble in everything, which means I know that this is going to be aqueous, and carbonate here is going to be our insoluble product in this case, our nickel 2 carbonate. This would be the balanced molecular equation. Any questions on that part of it? Now, since I sort of have it halfway done, we'll just continue on just to make sure about the other stuff that we talked about. We can go through this and break it apart into this total ionic equation. So the 2 that's here would come to the front here. We would have 1 carbonate. This guy here would also break apart, and we would have a nickel. The 2 for the chloride would come in front. Our 2 for the KCl would also get distributed. And remember that the solid here will stay together, and we would have NiCO3 solid. And again, this would be our complete ionic equation or our total ionic equation, whichever way you want to call it. And also, as we talked about, when we have this equation, we should be able to find some ions that look exactly the same on both sides. So I see 2 potassiums on both sides. I see 2 chlorides on both sides. And these guys, again, are our spectator ions, as we talked about. The spectator ions really there just to kind of balance out the charge. They're not really participating in the making of our product. And in this particular case, what we usually do is cross them out on both sides. And what that leaves us is the third type of equation we talked about last time, which is the nickel here is really going to come together with our carbonate. And it is going to form our nickel 2 carbonate solid on the other side. And this is the net ionic equation. So those were the 3 types of equations that we talked about in this particular problem. It just really wanted the overall equation there, the top one, the molecular equation. But again, your total ionic and your net ionic. When you do these, they should always be balanced. So if you look at each of the 3 equations that's on the screen there, they are balanced all the way through on both sides in terms of elements and also charge. So when you get to the very bottom there, our net ionic equation, overall charge on the left-hand side is 0, plus 2 minus 2 gives you 0. Overall charge on the right-hand side is 0. And we have 1 nickel on the left, 1 on the right, 1 carbon on the left, 1 carbon on the right, 3 oxygens and 3 oxygens on the right. So if you start with a balanced molecular equation and you distribute all the coefficients correctly, you should end up with a balanced total ionic equation and a balanced net ionic equation. Any questions on that there? Okay. All right. And so just going through it. All right, so why don't you take a second here and why don't you write the molecular equation for each of these and balance them. See what you come up with. Okay, so let's take a look. So we want to, again, the idea here is we want to make sure that we get the correct formulas first, since we don't have the product side. Again, in terms of recognition of the type of reaction, even though we're only talking about one so far. But again, you have a positive, negative guy, an ionic compound, a positive and a negative guy. So again, that should be a very big hint that this is a double displacement reaction. And again, you could just basically think about the two parts that make each of these up. So that's K plus and Cl minus. This is silver, which has that fixed charge of +1, and that's our nitrate, which is -1. So again, here our positive guys are going to switch partners, which means the K plus will come together with the NO3 minus, and that will give us KNO3, as we just need one of each. The silver will come together with the chloride here, and again, +1 -1 means we again just need one of each. So those are the correct products and the correct formulas. Then at this point, you want to make sure that if you are balanced. So if we look on the left-hand side, we have 1 potassium. Right-hand side, we have 1 potassium, 1 Cl, 1 Cl, 1 silver on the left, 1 on the right, and 1 NO3 on the left, and 1 NO3 on the right. So it actually is balanced. We also could use our solubility rules to help us predict the solubility of what's going on over here. So again, we see potassium, which is soluble in everything. And if that wasn't enough to convince you, the nitrate is also soluble in everything. So that is going to be aqueous. The silver chloride, again, chloride being soluble in everything except for 3 things, and silver happens to be one of those 3 things. So instead of chloride being soluble, because silver is there, it would be insoluble. And that would be our molecular equation. You could, if you wanted the net ionic equation, just so you know, you could kind of work backwards if you want. But here we'll go through the whole thing here. So this is our total here, plus and plus. On this side, we would have K plus and NO3 minus, all aqueous. I just didn't write it. Our spectator ions in this case would be our potassium and our nitrate on each side. Get rid of those, and that's going to leave us our net ionic equation, which would be the silver plus the chloride. Make sure silver chloride would be your net ionic equation. Again, didn't ask for it here, but that would technically be it. And this would be your total. If you put aqueous next to all those, that would be the right thing to do. And solid, obviously, here as well, aqueous. So I guess what I was going to try to point out here is if you're interested in perhaps just the net ionic equation, and you know what the solid is, for example, you can kind of work backwards and come up with the correct net ionic equation. Because if you start with that, you know that because of what it is, the formula here of silver is silver with a +1 charge and chloride with a -1 charge. So, you know, if you want to kind of quickly figure out the net ionic equation, you could actually work backwards, starting with the solid guy and basically just breaking it apart into its ions, and you probably will get the correct net ionic equation. So you don't necessarily have to go through each of the steps. If your goal is just the net ionic equation, you can almost kind of work backwards from the solid product, break it apart into its ions, and that will get you your net ionic equation. Any questions on that first one there? Looking at the second one here, we want to follow the same approach. Again, this is a positive, negative guy, positive and negative. So that should signal to you that this is a double displacement reaction. So again, here we want to start with the basic units here. And even though it's Na2, the basic unit of that is sodium with a +1 charge. The basic unit of sulfur there is a -2 charge. Calcium is a +2 charge. And chloride is a -1 charge. So again here, the important part is these guys are going to switch partners. So the sodium and the chloride are going to come together. Again, you want to start with the right formula, which would be NaCl, not Na2Cl2. So this would be the right one here. We then would put together our calcium and our sulfide. Plus 2 minus 2 gives us CaS. Now, at this point, we could balance it. We do have the 2 that needs to go here. Gives us 2 sodiums and 2 chlorides, and 1 calcium on each side and 1 sulfur on each side. So it is balanced at this point. We want to think about our solubility rules. So sodium chloride, as I was starting to write here, is going to be aqueous, right? Because it is sodium, which is soluble in everything, and chloride soluble in everything except for silver, lead, and mercury, which is not the case here. Now, what about calcium sulfide? If you go back and you look at your solubility rules there for calcium sulfide, you will find under sulfide that it is typically insoluble. But if you go across the column there, you will also see on that table that even though sulfur is typically insoluble, one of the exceptions actually is calcium, which means that this is also going to be soluble here. So what does that mean in terms of this reaction? So let's go through the total ionic equation. So if we do the total ionic equation, we would have 2 sodiums plus our sulfide plus our calcium and 2 chlorides. That means when we come to this side, we would have 2 sodiums because this guy would break apart. We would also have 2 chlorides, and we would have a calcium and a sulfide because that would also break apart. So when we look at everybody here, 2 sodiums on both sides cancel, spectator. Sulfide on both sides cancel, spectator. Calcium on both sides cancel, spectator. Chloride on both sides cancel, spectator. I just canceled out everybody that's there. That means basically when you mix these together, you still have just the ions floating around. Nothing's going to really happen. Not going to be any reaction, and technically speaking, no reaction would occur here because of that. Any questions on that? Again, they're basically all just in the solution, floating around kind of freely at this point. Any questions on that there? All right, any questions on how to write molecular equations, total ionic equations, net ionic equations? These are all obviously overall double displacement reactions. Ones that form a solid, again, can be classified also as precipitation reactions. Okay. All right, so I think one last one here, I think, so go for it. So just write the molecular equation here, see what you come up with. Okay, so again here we want to start with the two things that are reacting. Remember, again, even though there may be some more subscripts and stuff like that, what you want to think about is what makes up each of those things. So our ammonium sulfate is really made up of two things, and that is the ammonium ion and the sulfate ion, while lead 2 acetate is the lead 2 and the acetate. So again here, these guys are going to come together. These guys are also going to come together. And when we put them together, again, you want to use the basic units and put it together correctly to get the right formulas. So if you do that, on the other side there, you get the ammonium acetate, again, +1 and -1, even though the ammonium had a 2 on the other side. And you get the lead 2 sulfate, one of each of them coming together on the product side. Now, at this point, we could fix it by balancing it. So we would have to put a 2 in front of the ammonium acetate on the right, and that balances it out. So the last thing we could think about is our solubility rules here. So ammonium is soluble in everything. So right off the bat, we know the ammonium acetate on the right-hand side is going to be soluble. And the lead 2 sulfate, that is going to be insoluble in this case based on the solubility rules. And that would get us the solid product there. Any questions on how to write that equation? All right, so this is one sort of big aspect of double displacement reactions, which again are these precipitation reactions where we do form some type of solid. But not all double displacement reactions are really going to be a precipitation reaction or form a precipitation reaction. So we're going to talk about a couple other types of double displacement reactions and some other ways to classify them. So let's take a look at that next, I think. And that's what we've seen. Another important type of reaction, which most of the time is a double displacement reaction, is a reaction between an acid and a base. And let's talk a little bit about what an acid is. An acid is something that in water basically will be able to produce H+ ions. So those are hydrogen ions. When it does react with water, and you'll learn more about it in the next class if you take it, when you're talking about acids and bases, H+ and what we see below there, H3O+, which is the hydronium ion, are essentially considered equal to each other. They're basically kind of the same thing when you're dealing with acid and bases. So H3O+ is the hydronium ion, H+ is the hydrogen ion, and again, they are used sort of interchangeably, especially dealing with acid and base sort of chemistry. Again, if you take 200B, there's a whole chapters on that, and you'll see a lot of that sort of used interchangeably. And that's really the definition of an acid, is it's the ability to produce that free H+ in solution. So that's the key to what makes something sort of a strong acid. A weak acid, not an acid, is really that ability to produce not just H+ is attached to anything, but it needs to be free H+ to be released free into the solution, is really what makes it an acid. It's also what affects the pH of the solution, is how much of that free H+ is basically floating around in the solution. A base, on the other hand, is basically something that will be able to form hydroxide or OH- in solution. And that also is sort of the same idea. It's not OH- that's attached to anything, but it's the ability to produce and let the OH- become free in the solution and basically floating around. And the amount of OH- and H+, they're actually related to each other. So as one goes up, the other goes down. So that's a lot to do with sort of the pH, the acidity of a solution, is whether or not the amount of H+ or OH- that's present, and they actually are pretty much tied to each other. So as one goes up, the other does go down. So typically when we take an acid and a base, we typically will get two things that are formed. One thing is water, and water is basically generated from the acid because the acid produces H plus, and the base produces OH minus. And H plus and OH minus have a very strong attraction to each other. And did I write aqueous next to that? I did. I'm supposed to write base. There, try that again. Base. The H plus and OH minus has a very strong attraction to each other to form water. And as we'll see, the overall reaction of really what is happening a lot of times when you take an acid and base together is the formation of water, which is why, especially when you take a strong acid plus a strong base, these are sometimes what is referred to as a neutralization reaction. Acid-base neutralization reaction. And it's really basically called that because the formation of water is essentially what's happening. And a salt is a fancy word. I'm not really sure how fancy it is, but it is a word that basically just means an ionic compound. So you oftentimes hear somebody say salt and water. Again, the salt coming from the acid and base, and water also coming from the acid and base when you put these together. So here is some common acids. There's some strong acids. By the way, these are some strong acids here. As you can see over there. Some other strong acids, HBr, HI is also a strong acid. There's some moderate acids there, and then some weak acids as you come down this way, acetic acid, HF, and so forth. There's some strong bases. A lot of strong bases come from group 1 and 2 on the periodic table. Again, group 1, right, is the alkali metals. Group 2 is the alkaline earth metals. And when somebody says alkaline, it means basic. So that's where a lot of strong bases come from. A lot of strong bases actually have hydroxide in the formula. And they're strong electrolytes, so they break apart. The sort of version of ammonia that we oftentimes use in liquid is what's known as ammonium hydroxide, but ammonia really is the weak base here. So in an acid-base neutralization reaction, if we take hydrochloric acid like we have here, and we take sodium hydroxide, ultimately, if you just look at this, this is really a double displacement reaction because HCl is H plus and Cl minus, so positive, negative, Na plus and OH minus. And really what's going to happen is they're going to switch partners. So the H plus and the OH minus are going to come together to form your water. The Na plus and your Cl minus are going to come together to form your salt. So this would be my salt. This would be my water in this particular reaction. And if we break this apart, just like we did with our double displacement reactions earlier and our precipitation reactions, the HCl, which is a strong acid, would 100% break apart into H plus and Cl minus. The sodium hydroxide, which is a strong base, will 100% break apart into Na plus and OH minus. On the other side, our sodium chloride, based on solubility rules, is going to be soluble and break apart. Now, this is water, right, which is a liquid. And again, a liquid will stay together just like a solid. Again, all of these are aqueous. And if you look at this, you can see the same thing that we saw in our precipitation reaction is we have some ions that look exactly the same on both sides. That's going to be our sodium ion and our chloride ion on each side. Those are spectator ions. And if we get rid of them just like we did before, what we are left with is our net ionic equation, which is right here, for what is really happening in this reaction. It is the H plus from the acid coming together with the OH minus from the base to form water. And that is our net ionic equation. No matter what combination of strong acid, strong base that you put together, when you get all the way down to the net ionic equation, it's always going to be H plus OH minus makes H2O. This is our net ionic equation. This is something that, honestly, if you physically did it, you would not be able to see it, right? So unlike a precipitation reaction where you mix it together, you see that yellow solid form. When you mix these two together, it's going to look like nothing happened. But actually something did happen. You actually formed water. And so visually, you can't really kind of see it, but it is sort of happening here. So again, no matter what combination you did, if you took, say, nitric acid, which is a strong acid, and you put it together with KOH, which is a strong base, again, a double displacement. Really, if in an acid base, if you could recognize this, the H from the acid, the OH from the base, going to give you your water. The K, which is K plus, and the nitrate is going to come together to make KNO3. And again, if we broke this apart, this would be H plus NO3 minus plus K plus OH minus makes our H2O, which is a liquid. So again, a liquid is going to stay together. Our K plus and our NO3 minus. NO3 minus on both sides, spectator. K plus on both sides, spectator. Look at that. We have H plus and OH minus, making our net ionic equation here of water. So your net ionic equation here is basically the formation of water. And again, that is ultimately what is happening when we take a strong acid and strong base together, is basically that formation of water is truly the reaction that is taking place. Even though visually, like I said, if you looked at a test tube or a beaker, you might not see much happening, but sort of on the microscopic level, you are forming water. And again, this is why it is called a neutralization reaction, because really the overall reaction is that formation of water. Any questions on that there? So this is an acid-base reaction or an acid-base neutralization reaction. This can also be classified under the big umbrella of double displacement reactions. So as you can start to see, and as you may know, there are many ways you can sort of classify reactions depending on what you're looking at. So far we've seen this big classification of double displacement reactions, and sort of underneath there, a way you could also classify that type of reaction is a precipitation reaction. If you make a precipitate or a solid, you also can put underneath that double displacement umbrella the acid-base neutralization reactions, which ultimately forms water. So again, sort of that big classification is that double displacement classification. Here's in sort of picture form what we were just talking about. And again, you can see here when you add all this together, you know, there's not much going on there in sense of I see something happening, but it is happening. As you can see, it is forming water, and basically that salt that's in there, and a reaction is taking place. Now, another sort of double displacement reactions that occur. So far we've seen some double displacement reactions that make solids. We've seen some double displacement reactions that make water. There's also double displacement reactions that actually can produce gases. So a gas can sometimes be a product of a double displacement reaction. And what we're going to see here is sometimes a gas will be made sort of directly as a direct result of a reaction happening. And sometimes the gas actually will be made as a result of a product going through another reaction. So one sort of a direct formation of a gas, and one is sort of an indirect formation. And with that was a very quick conversation. Let's go back and look at it and sort of see what's happening here. So in the first one, we take some K2S, some potassium sulfide. And again, just to show you it's a double displacement, that's a positive negative guy. Our H2SO4, which is sulfuric acid, is also positive negative. Remember that an acid is really H plus as the cation, as we talked about, right? And some type of negative anion. So that's how you could think of acids, and that's why we think of it like this double displacement. Again, what's going to happen is the K plus and the SO4 2 minus will come together to make this K2SO4. And then the H plus and the S2 minus will come together to make our H2S, which is our hydrogen sulfide gas. This is a gas, not the acid that we talked about when we were talking about nomenclature, because it doesn't have the aqueous symbol next to it. Remember, if that had the aqueous symbol, that would be hydrosulfuric acid. But here, because it's a gas, it's called hydrogen sulfide gas. Smelly, toxic, deadly gas, which, you know, you play with in 200B. No, I'm just kidding. Sort of. But this is a direct generation of that gas. And you can see by that product there, this is what happens. And if you went through all your sort of total ionic equation and your net ionic equation, remember this would not break apart. So you would be left with something like 2H plus S2 minus makes the H2S. Now, sometimes what happens when you do this double displacement reaction, like we have here as well, positive, negative, we do get our K2SO4 just like above, but in this case, because this is sulfite instead of sulfide, what we get is this guy here, which is aqueous. It is H2SO3. This is sulfite sulfurous acid. So instead of a gas being made, we actually made this acid. Now the deal with this acid, and there's a couple of acids like this, is they do not hang around a very long time. And almost immediately, this guy will go through another reaction where it will generate SO2 gas, which is like bubbles and stuff that you see. And this reaction, as we'll talk about, is actually what is known as a decomposition reaction. And basically in a decomposition reaction, as we'll talk about, you start with one thing and it basically breaks apart into two or more things. So in a sort of non-direct production of a gas, you have a double displacement reaction that occurs first, which is this guy here, this double displacement reaction, followed by a decomposition reaction that occurs from one of the products, and it's that secondary reaction that actually is what is generating the gas. But it all sort of starts from the double displacement reaction, followed by that secondary reaction. So the first one there is a direct formation of a gas. The second one is sort of an indirect formation, but this does occur pretty quick. Another very common one is something like if you take hydrochloric acid or some type of acid, add it to something like sodium carbonate, you will get some sodium chloride plus some H2CO3. And put a 2 there, I think, and a 2 there to balance it out. Now, what we form here is what is known as carbonic acid, and very much like this guy here, carbonic acid almost immediately, or pretty much immediately, will also go through a decomposition where it makes water and CO2 gas. And that's like the plop, plop, fizz, fizz that you sometimes see, like Alka-Seltzer and that type of stuff. Similar type of reaction, not exactly the same thing, but sort of idea. If you've ever done this reaction, it just starts to bubble really quick, and that's the CO2 being produced in that reaction. So again, that's another example of a double displacement reaction, which was the first reaction there, followed by a decomposition reaction to produce a gas. So that's sort of a very common sort of two-shot approach, I guess, to make a gas or a gas being produced. Any questions on that? And that is what we see here. This is sodium bicarbonate, same effect here. When you do it, you see all these bubbles and stuff starting to form, and all that is the CO2 gas being made almost instantly as that carbonic acid, which is basically where these two guys came from, decomposes and produces that CO2. So here's a table that sort of summarizes some reactions, double displacement reactions, that will result basically in a gas being formed. So if you take any type of metal that has sulfide in it, like K2S, and you react it with an acid, you will produce H2S, which is hydrogen sulfide gas, and that will be a direct sort of production of it. So it will be formed directly from that production. If you take a metal like I just did in the one I wrote, which was like sodium carbonate or potassium carbonate, like in this example here, and you react it with an acid, it will make that carbonic acid, which will then go through a decomposition reaction and produce CO2 gas. If you have a metal that's with sulfite and react it with an acid, it also will produce something like sulfurous acid, which will go through a decomposition reaction to produce SO2. And if you have something with ammonium in it and react it with a base, it will basically produce ammonium hydroxide, which ultimately will produce ammonia through a decomposition reaction, basically. So this is a nice table. It sort of summarizes some of the big sort of gas-producing reactions. Again, these are double displacement reactions that are producing gases either directly or indirectly. So we've seen this big umbrella of double displacement reactions that actually produce sort of three types of reactions, if you will, underneath that. Again, that precipitation reaction where a solid is formed, that acid-base reaction where water is formed, and here we see really double displacement reactions that the end result is the formation of some type of gas. Any questions about sort of double displacement reactions or any of those things that we've been talking about? All right. So now that we have sort of that big double displacement umbrella and the reactions that fall underneath those, we're now going to talk about really another sort of big umbrella in terms of types of reactions that occur. And these are what are known as redox reactions. And redox reactions are sometimes what are referred to as redox reactions. And redox reactions are basically oxidation reduction reactions. And basically it's a transfer of electron. So ultimately for a chemical reaction to occur, there's sometimes what is referred to as sort of driving forces for a chemical reaction to occur. And some of the basic driving forces for a chemical reaction to occur is the formation of a solid, like we just saw in the precipitation reactions, the formation of water, just like we saw in the acid-base reactions. And the third really big sort of driving force for a reaction is the transfer of electrons, which is sort of what we're going to be talking about here in our redox reactions as electron transfers. So there's basically two things. These two things always occur together. If something is being oxidized, something will be reduced. So they do sort of go together. So what does oxidation mean? What does reduction mean? If something is oxidized, as it basically shows down there, or oxidation, I guess, it has lost electrons. I'll go with oxidation. Reduction means that something has gained electrons. Sometimes people remember this by Leo the lion goes grr. loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig. Oxidizing is losing, reducing is gaining. So again, those are a couple ways you can sort of remember oxidation, reduction. You don't want to choose, put Leo the lion on the oil rig and he'll go grr, so you don't have to choose. You can use them both if you like. But what does that mean in terms of sort of what is going on in terms of charge, or really what's known as oxidation state? So when something loses electrons, they actually become more positive. And the easiest way sometimes to sort of figure out, is this thing going through oxidation? Is this thing going through reduction? Is you could use really just a basic number line. Yeah. To the right there is positive, right? Negative numbers. So if you lose electrons, you become more positive and go through oxidation. And if you gain electrons, which are negative, you're going to become more negative and go through reduction. So you literally can use sort of a number line and go, which way am I moving? And you could kind of figure out, you know, is it going through oxidation? Is it going through reduction? So if we look at, we'll start actually this way. We'll start with the whole reaction here, the overall reaction. And if we look at that, the magnesium here by itself, uncombined, solid magnesium, has an oxidation state of 0. And that's usually what is called as the oxidation state. It's not really necessarily the charge, and we'll talk about that in a little bit here in this chapter. Although it looks like a square, that is supposed to be a 0. The oxygen, which is O2 by itself, no charge associated with it, no oxidation state, it's 0. Remember that things only really do get charges when they kind of come together, a metal and a non-metal. And that's what happens over here. The magnesium over here in this state actually has the +2 charge. And the oxygen in this state has a -2 charge. And that is truly where they get their oxidation state and their charges from. So when we're trying to determine if we had an overall reaction, what is being oxidized and what is being reduced, we could look at those oxidation states and figure out what's going on. The magnesium started at 0, so this is where you could use your number line if you like. We can magnesium actually started at 0 and ended at +2, which means it is going in this direction, which means that the magnesium here, as you can see, is going through oxidation. Now, if we do the same thing for our oxygen started at 0 and ended at -2. So again, if you go to your number line here, it started at 0 and ended at -2, which is in this direction. And that is the direction of reduction. And as you can see here, the oxygen went through a reduction. So we could actually split this reaction off into what are known as half reactions. And half reactions is one reaction that shows you the oxidation reaction that's occurring, and one reaction that shows you the reduction reaction that's occurring. So the magnesium here, again, started at 0, ended at +2, going through oxidation. And this would be the oxidation half reaction. Because it has lost electrons, when you write an oxidation half reaction, the electrons find themselves on the product side. So electrons are a product in an oxidation half reaction because they're thought of as being lost or are given off. So they end up on the product side. And that would represent our balanced oxidation half reaction. In case you're curious, the 2 comes from here, from the balanced overall equation. And this is a balanced half reaction, just like what we were talking about a second ago. If you look at that half reaction, you have 2 magnesiums on each side. So that's balance. The overall charge on the left-hand side of the arrow is 0. The overall charge on the right-hand side of the arrow is actually 0. 2 times plus 2 is plus 4. Plus the 4 electrons gives us minus 4, which gives us 0 overall. The second one here is the reduction half reaction. And the reduction half reaction, you see the electrons on the reactant side. And that indicates that it is a reduction reaction where it is gaining electrons. So those oxygen is gaining the electrons and forming that -2 charge on the product side. You may also wonder, well, is a magnesium +2? Why is there 4 electrons? And it's because we don't have, in this case, just one magnesium. We actually have 2. And each magnesium is basically going to give up 2 electrons. So both of them will give up a grand total of 4 electrons. So that's why we have the 4 there to balance out everything. And again, the bottom half reaction is also balanced. There is 2 oxygens on each side. The overall charge on the left is -4, and the overall charge on the right is actually -4. So it actually is balanced as well. Also brings up a good point when you talk about redox reactions. In terms of the charge, it does need to be balanced on both sides of the arrow, but it does not always necessarily have to be 0 in terms of that number. So it doesn't always have to be 0. It just needs to be the same number basically on both sides. That is what is referred to as the reduction half reaction. And that is because if you add both of these reactions back together, which is what you get here. And when you add reactions back together, basically what you do is everything on the left-hand side of the arrow stays on the left-hand side of the arrow. Everybody on the right-hand side of the arrow in both of those equations stay on the right-hand side of the arrow. And you get this one. And what should always happen when you add the half reactions together, the electrons should always cancel. So to have a properly balanced half reaction, both the oxidation and reduction half reaction, you should always have the exact same number of electrons in each, because it is a complete transfer of electrons. So whatever electrons that are lost in the oxidation step should be the exact same electrons that are gained in the reduction step along the way. And what you're left with when you add those together is the overall reaction here that's on the bottom. Any questions on that? So redox reactions a lot of times involve sort of electrochemistry. And if you look in these pictures, aqueous guys that have charges. So all of our guys that have charges are usually the guys floating around in the solution. When they lose the charge or become solid, they end up as this sort of solid that you can see plating on these metals here. And again, that's sort of what's happening here. Anything with a charge and sort of redox reactions usually will be aqueous and floating around. Anything that becomes sort of a solid obviously will not be floating around in solution. And as you can see in this case, gets plated on the metal in that case. So again here, if we look at this reaction, this is a redox reaction. If we look at sort of the oxidation numbers that are happening here, this is 0. Again, this is zinc in a standard state. This copper 2 sulfate is copper with a +2. Sulfate is a -2 overall. The zinc on this side does gain a charge, is +2. The sulfate still -2, and the copper here is 0 when it goes through this. Now, again, if you're not sure what's going on, you could use that number line to determine. And if you use that number line, what you will see is again, more positive oxidation and reduction heading this way, right? So if we look at the zinc went from 0 to +2. So the zinc started at 0 and went to +2, which is going in this direction. So the zinc is actually going through oxidation. If we look at the copper started at +2 and ended at 0, which means the copper started down here and ended this way, which is going through reduction. And again, you can see that that is what's happening. We could write the two half reactions for that, and it will look something like this, that the zinc is losing 2 electrons. So again, electrons on the product side, and the zinc is being oxidized, again, going from 0 to +2, while the copper here is gaining electrons and going through reduction, and the copper going from +2 to 0 and being reduced. Now, this brings up another good point of what we talk about when we talk about oxidation and reduction, and that is what is the reducing agent and the oxidizing agent. Now, the reducing agent and the oxidizing agent are different than what is being oxidized and what is being reduced. So, as strange as it may sound, the reducing agent is the substance that gets oxidized, while the oxidizing agent is the substance that gets reduced. So when you're talking about the agents, the oxidizing agent, the reducing agent, it's actually the opposite of the name. So why is that? It is because zinc is the reducing agent. Now, in order for something to be reduced, something has to gain electrons. So because zinc loses electrons, it's providing the electrons for copper to gain, and thus it is the reducing agent for copper. While the oxidizing agent, in order for something to be oxidized, something has to lose electrons so somebody could gain them. So the copper is the guy that's going to gain the electrons, and the only way you could gain the electrons is to cause zinc to be oxidized. So it is what is known as the oxidizing agent. So sometimes that confuses people. The agents, the easiest way to remember it, if you're asked what is the reducing agent or what is the oxidizing agent, is to figure out what is being oxidized and what is being reduced. And again, it's opposite of the name. So the reducing agent would be the substance being oxidized. The oxidizing agent would be the substance that is being reduced. By the way, the oxidizing agent and the reducing agent are always found on the reactant side. So in our case, it would be the zinc, and the copper 2 is the oxidizing agent and reducing agent. You should not just write zinc with no charge or copper with no charge, because again, or I'm sorry, you shouldn't write, I guess in general, the way what I'm trying to say is you shouldn't just write zinc or copper, because that really doesn't imply, what is oxidizing agent, reducing agent. You really do want to specify, for example, in this case, that guy and this guy for the other one. So if it does have a charge like the copper does, you should write copper 2, not just Cu, because that might be the guy on the product side. So you do want to really specify it. You may also notice that in this reaction here, the sulfate, nothing is really happening with the sulfate here. The sulfate, in terms of charge on each side, remains unaffected. So it's not really participating. It is really, believe it or not, like a spectator ion. So if you were to write the net ionic equation for this guy, just kind of like what we did with double displacement reactions, you would have the zinc, which is a solid, which would stay together. You would take the copper 2 and break it apart into this and this. The zinc sulfate would also break apart. And the solid copper would stay together. So in this thing, the only spectator ion is actually the sulfate, which is why nothing is really happening with the sulfate. And what we will see is the net ionic equation of really what's happening is the zinc, the solid, and the copper here that has a +2 charge is going to form the zinc with a +2 charge, and the copper with no charge on this side. And this is really what is sometimes referred to as the net ionic equation for this redox reaction. It gets down to the basics of what's happening. The zinc is going from an oxidation state of 0 to +2, losing electrons, being oxidized. The copper is going from +2 to 0, being reduced. And as we'll talk about, since we're getting to the end here, next time as well, even though this is technically a redox reaction, as we will see, this is also what is referred to as a single replacement reaction, where we have one thing coming in and kicking out the other. So if you remember in one of those earlier experiments, we sort of touched upon single replacement reactions, but that also is what is happening here. So as we've seen, and as we talked about with double displacement reactions, the big umbrella kind of individual classifications as you could do. Here, redox reactions, which is what we're talking about here, is the big umbrella. This will be, as we'll see later on in the chapter here, also can be classified as a single replacement reaction as well. Any questions on that there? All right, so I think we'll probably lay it up here for today. Maybe a good stopping place. Any questions on anything we talked about here today? Are you, I'm not sure I understand exactly your question in terms of, so if you're asking, for example, something like this, like if you're taking that and you want to convert it into like ions for a total ionic equation, if that's what you're asking, the 2 here, when you would convert it into the total ionic. Yeah, so, okay, so yeah, so if you're going to break a formula like this as ionic into, say, a total ionic equation or the ion, the 2 that's here does go into the front because, again, the basic unit of something like sodium, for example, is Na+. And basically what this 2 means is that you have 2 of those Na pluses. Remember that there is no real ion formula that looks like this. So it would come like that. If you had something like calcium nitrate, which I think is what you're talking about. Yeah, like that, maybe? Okay. So if you have calcium nitrate, same idea. When this would break apart, say for the total ionic equation, this is really calcium. The ion here is really nitrate, which is NO3 minus. And again, this 2 means that you technically have 2 of them. So when you break it apart into total ionic equation, that subscript usually will come to the front of the formula. The only time you wouldn't obviously bring a subscript to the front is, for example, this 3. That's actually part of the formula, so that obviously doesn't go to the front or anything like that. Yeah, the 3 would not for nitrate, because nitrate is this, right? So that is nitrate, and this whole thing stays together. So if you had any type of formula that had nitrate in it, you know, if you had a 3 in there, the 3 would go in the front, but the 3 is from the outside of the parentheses and stuff like that. And nitrate would never have a 3 on top because it's only -1 charge. Other questions on that? Okay. So we'll take a break and we'll do lab there at 9:45. Yeah. All right. Make sure you put here if you didn't do so, and I'll see everybody in about 20 minutes. Lab today, I believe, is 8. I believe. Yes. I think it should be experiment 8.